A quantum computer?
It's always been the case that technology moves fast. However, lately the advancement in technology has been nothing short of extraordinary, and even the people at the forefront of the advancement are scared, like Google recently shutting down its quantum computer because of something terrifying that is happening. How did Google arrive at this point, and what exactly has Google invented? Stay tuned to find out. Quantum computing is one of the hottest topics today. It is a rapidly emerging technology that harnesses the laws of quantum mechanics to solve problems too complex for classical computers. If you're not used to everything high-tech, quantum mechanics describes the behavior of matter and energy at the smallest scales, where particles such as electrons and photons can exist in superposition, a combination of two or more states, and entanglement, a correlation between two or more particles. Quantum computing uses these phenomena to encode and manipulate information in quantum bits, or qubits, which are the basic units of quantum information. The history of quantum computing can be traced back to the 1980s, when physicists such as Paul Benioff, Richard Feynman, and Yuri Manin proposed the idea of using quantum systems to perform computations. They realized that quantum computers could potentially exploit the parallelism and interference of quantum states to solve certain problems faster than classical computers. One of the first models of a quantum computer was developed by David Deutsch in 1985, who showed that a universal quantum computer could simulate any physical process. Quantum computing works by applying quantum logic gates to qubits, which are usually implemented using physical systems such as superconducting circuits, trapped ions, photons, or atoms. Quantum logic gates are operations that change the state of one or more qubits according to certain rules. For example, a NOT gate flips the state of a single qubit from 0 to 1 or vice versa, while a CNOT gate flips the state of a second qubit only if the first qubit is 1. By combining multiple quantum logic gates, one can create quantum algorithms that perform specific tasks on qubits. Quantum computing is different from classical computing in several ways. First, quantum computing uses qubits instead of bits, which can store more information than just a 0 or 1. A qubit can be in any superposition of 0 and 1, meaning it can have a certain probability of being either state. For example, a qubit can be in a state of 0.6 ket 0 plus 0.8 ket 1, where ket 0 and ket 1 represent the basis states of 0 and 1 respectively. This means that the qubit has a 36% chance of being measured as 0 and a 64% chance of being measured as 1. A classical bit can only store one value at a time. Second, quantum computing uses entanglement to create correlations between qubits, which can enhance the computational power of quantum algorithms. Entanglement is a phenomenon where two or more qubits share a quantum state and behave as one system, even if they are physically separated. This means that if one qubit is measured as 0, the other qubit will also be 0 with certainty, and vice versa. Entanglement allows quantum algorithms to manipulate multiple qubits at once and exploit their correlations to achieve speedups over classical algorithms. Third, quantum computing uses interference to amplify the desired outcomes and suppress the undesired ones. Interference is a phenomenon where two or more quantum states combine to form a new state depending on their relative phases. For example, two states with the same phase will add up constructively, while two states with opposite phases will cancel out destructively. Quantum algorithms use interference to increase the probability of measuring the correct answer and decrease the probability of measuring the wrong answer. This requires careful design of the quantum logic gates and their sequences to create constructive and destructive interference patterns. Quantum computing is better than classical computing for some problems that involve large amounts of data, complex calculations, or optimization. For example, quantum computers can factor large numbers faster than classical computers using Shor's algorithm, which has implications for breaking encryption schemes based on RSA or Diffie-Hellman. Quantum computers can also search large databases faster than classical computers using Grover's algorithm, which has implications for data mining or machine learning. Quantum computers can also simulate quantum systems more efficiently than classical computers using various methods such as variational quantum eigensolvers or quantum phase estimation, which has applications for chemistry, physics, and biology. Here are some examples of how quantum computing is better than the normal computing you're used to. Factoring large numbers. One of the most famous applications of quantum computing is Shor's algorithm, which can factor a large number into its prime factors in polynomial time, while the best classical algorithms take exponential time. This has implications for cryptography, as many encryption schemes rely on the difficulty of factoring large numbers. Searching unsorted databases. Another well-known quantum algorithm is Grover's algorithm, which can search an unsorted database of n items in O square root n time, while the best classical algorithm takes O n time. This can be useful for finding the proverbial needle in a haystack or a matching record in a large database. Simulating quantum systems. Quantum computers can naturally simulate other quantum systems, such as molecules, atoms, or particles, while classical computers struggle to model the complex interactions and dynamics of quantum systems. This can enable advances in chemistry, physics, biology, and materials science, as well as the design of new drugs and materials. Optimizing combinatorial problems. Quantum computers can also tackle hard optimization problems, such as the traveling salesman problem or the knapsack problem, which involve finding the best solution among a large number of possible solutions. Quantum computers can use techniques such as quantum annealing or quantum approximate optimization algorithms to find near-optimal solutions in less time than classical computers. Machine learning and artificial intelligence. Quantum computers can also enhance machine learning and artificial intelligence applications, such as classification, clustering, regression, or reinforcement learning. Quantum computers can leverage quantum data structures such as qubits or quantum neural networks to store and process more information than classical bits or neurons. Quantum computers can also use quantum algorithms such as quantum support vector machines or quantum principal component analysis to perform faster and more accurate computations than classical algorithms. Now, Google's quantum processors are one of the most advanced and promising technologies in the field of quantum computing. They use superconducting circuits to create and manipulate qubits, the basic units of quantum information. Superconducting qubits have several advantages over other types of qubits, such as high coherence times, fast gate operations, and scalability. One of the challenges of quantum computing is to design and implement algorithms that can take advantage of the quantum properties of qubits, such as superposition and entanglement. And to address this challenge, Google developed a framework called Cirq, which allows users to program and simulate quantum circuits on Google's quantum processors. Cirq is an open-source Python library that provides a simple and intuitive interface for creating and manipulating quantum circuits. Cirq also supports various quantum hardware platforms, such as Google's Sycamore processor, which achieved quantum supremacy in 2019 by performing a task that would be impossible for a classical computer. Cirq enables users to explore various aspects of quantum computing, such as error correction, noise mitigation, optimization, and benchmarking. Cirq also integrates other tools and frameworks, such as TensorFlow Quantum, which allows users to apply machine learning techniques to quantum data. One amazing thing about Google's quantum processors and Cirq is that they're paving the way for the development of novel and powerful applications of quantum computing, such as cryptography, optimization, artificial intelligence, and quantum chemistry. By using superconducting technology and providing an accessible and flexible framework, Google is making quantum computing more feasible and accessible for researchers and developers around the world. Another remarkable quantum computing achievement by Google came in 2019 when Google's Sycamore performed a calculation in 200 seconds that would take a classical supercomputer 10,000 years to complete. This was a demonstration of quantum supremacy, the point at which a quantum computer can outperform any classical computer on a specific task. Quantum supremacy is a milestone for quantum computing, a field that promises to revolutionize many areas of science and technology. So how did Sycamore do it? It used 53 qubits, the basic units of quantum information, to generate a random sequence of bits that follows a certain distribution. This task is easy for a quantum computer because qubits can exist in a superposition of two states, 0 and 1, at the same time. This means that qubits can explore multiple possibilities simultaneously, giving them an exponential advantage over classical bits that can only be either 0 or 1. And this specific task would be extremely hard for a classical computer because it would have to simulate all the possible states of the qubits and their quantum interactions, which grow exponentially with the number of qubits. The best supercomputer in the world, Summit, would need 10,000 years to perform this simulation, according to Google's estimate. But Sycamore did it in just over 3 minutes with high accuracy and fidelity. This achievement was hailed as a breakthrough for quantum computing, but also sparked controversy among some experts. IBM, one of Google's competitors in quantum computing, challenged Google's claim of quantum supremacy. IBM argued that Summit could perform the same task in 2.5 days with an improved algorithm and more memory. IBM also questioned Google's definition of quantum supremacy, saying that quantum computers will never reign supreme over classical computers, but will rather work in concert with them. Google, however, defended its claim of quantum supremacy, saying that its calculation was not only faster but also more complex and realistic than IBM's proposed simulation. Google also said that quantum supremacy is not about comparing quantum and classical computers on arbitrary tasks, but about showing that quantum computers can do things that are beyond the reach of classical computers. The debate over quantum supremacy is not settled yet, but it shows how much progress has been made in quantum computing and how much more is still to come. Quantum computers have the potential to solve problems that are intractable for classical computers, such as finding new drugs, optimizing logistics, breaking encryption, and advancing artificial intelligence. Google's quantum supremacy experiment has given us a glimpse of the future. And another software tool that Google provides is TensorFlow Quantum, an open-source library for hybrid quantum classical machine learning. TensorFlow Quantum integrates Cirq with TensorFlow, the popular machine learning framework, and allows users to construct quantum data pipelines and quantum neural networks. For quantum chemistry applications, Google has developed OpenFermion, an open-source library for compiling and analyzing quantum algorithms to simulate fermionic systems, such as molecules and materials. OpenFermion can interface with Cirq and TensorFlow Quantum to implement various quantum chemistry methods, such as variational quantum eigensolvers and quantum phase estimation. Google's software tools are designed to work with Google's hardware platforms, which are among the most advanced quantum processors in the world. Google's latest quantum processor, Sycamore, has 54 superconducting qubits and can perform operations with high fidelity and low crosstalk. Sycamore was used to demonstrate quantum supremacy, as mentioned before, in 2019 by performing a calculation that would be impractical with classical computers. Google is also working on developing new hardware architectures and techniques to improve the performance and scalability of quantum processors. For example, Google is exploring topological quantum states, which are robust against local errors and can enable fault-tolerant quantum computation. Google is also investigating quantum error correction schemes, such as repetition codes and surface codes, to protect logical qubits from noise and decoherence. Google's quantum computing research is conducted at the Quantum AI campus in Santa Barbara, California, which houses a state-of-the-art quantum data center, fabrication facility, research lab, and workspace. The campus is home to a team of world-class researchers and engineers who collaborate with academia and industry partners to advance the field of quantum computing. Google's vision is to build the world's first fault-tolerant quantum computer and develop novel quantum algorithms to help solve near-term applications for practical problems. By offering software tools and libraries for quantum machine learning and quantum chemistry, Google aims to empower researchers and developers to explore the possibilities of quantum computing and discover what lies beyond classical computing. Google continues to make big moves in quantum computing and artificial intelligence. The tech giant has announced that it will build a quantum AI campus in Santa Barbara, California that will house a quantum data center, a fabrication facility, a research lab, and a workspace for its quantum team. The campus will be the home of Google's quantum AI division, which is led by John Martinez, a former professor at the University of California, Santa Barbara, and one of the world's leading experts in quantum computing. The quantum data center will host Google's quantum processors, which are devices that use the principles of quantum mechanics to perform calculations that are impossible or impractical for classical computers. The quantum data center will allow Google to scale up its quantum computing capabilities and run more complex and powerful algorithms. The fabrication facility will be where Google will design and manufacture its quantum processors and other components. This will give Google more control and flexibility over its quantum hardware and enable it to experiment with different architectures and materials. Google will also collaborate with external partners and researchers to share its fabrication expertise and resources. The research lab will be where Google will conduct cutting-edge research in quantum computing and artificial intelligence. Google has a strong reputation in both fields and has published many influential papers and breakthroughs. The research lab will foster innovation and collaboration among Google's quantum scientists and engineers, as well as with academic institutions and other organizations. Some of the topics that Google will explore include quantum error correction, quantum machine learning, quantum optimization, quantum chemistry, and quantum cryptography. And the workspace will be where Google's quantum team will work together and interact with each other. The workspace will be designed to create a stimulating and inspiring environment for the quantum team, which consists of more than 100 people from various backgrounds and disciplines. The workspace will also host events and workshops in the quantum community, such as hackathons, seminars, and training sessions. Google's quantum AI campus in Santa Barbara will be completed by 2024. It will be a major milestone for Google and for the field of quantum computing and artificial intelligence. Google hopes that by building this campus, it will accelerate the development of quantum technologies and applications that can benefit humanity and society. One of the main applications of quantum computing for AI is machine learning, which is the process of learning from data and making predictions or decisions based on it. Machine learning algorithms often rely on linear algebra operations such as matrix multiplication and inversion, which can be sped up by quantum computers. Google has developed several quantum machine learning algorithms such as quantum neural networks, quantum support vector machines, and quantum principal component analysis that can leverage the power of quantum computers to learn from large and complex data sets. And another application of quantum computing for AI is natural language processing, NLP, which is the branch of AI that deals with understanding and generating natural language. NLP tasks include speech recognition, machine translation, sentiment analysis, and text summarization. Google has been exploring how quantum computers can help with NLP tasks, such as by using quantum annealing to find optimal solutions for word embeddings, which are numerical representations of words that capture their meanings and relations. Google has also proposed a quantum algorithm for text generation, which can produce coherent and diverse text based on a given prompt. A third application of quantum computing for AI is computer vision, which is the branch of AI that deals with analyzing and interpreting visual information. Computer vision tasks include face recognition, object detection, scene segmentation, and image synthesis. Google has been experimenting with how quantum computers can enhance computer vision tasks, such as by using quantum convolutional neural networks to perform image classification, which can recognize what objects are present in an image. Google has also demonstrated a quantum algorithm for image generation, which can create realistic and novel images based on a given input. Google's vision is to create a scalable and universal quantum computer that can tackle any problem that is beyond the reach of classical computers. By applying quantum computing to AI, Google hopes to unlock new possibilities and discoveries in various domains such as science, medicine, engineering, and art. Google believes that quantum computing and AI can work together to create a positive impact on humanity and society. However, quantum computing also faces a major challenge: decoherence. Decoherence is the loss of quantum coherence, the process in which a system's behavior changes from that which can be explained by quantum mechanics to that which can be explained by classical mechanics. Decoherence occurs when a quantum system interacts with its environment, such as noise, heat, or electromagnetic fields, and becomes entangled with it. This causes the quantum system to lose its superposition of states, a key feature that allows quantum computers to perform parallel computations and achieve exponential speedups over classical computers. Decoherence is a serious problem for quantum computing because it limits the time and accuracy of quantum operations and algorithms. If decoherence happens too quickly or too strongly, the quantum computer will lose its advantage over classical computers and produce erroneous results. Therefore, it is crucial to find ways to protect quantum systems from decoherence and extend their coherence times. This can be done by using various techniques such as error correction codes, fault-tolerant architectures, dynamical decoupling methods, and optimal control strategies. Google is currently working on several aspects of decoherence control in quantum systems, both theoretically and experimentally. For example, Google's quantum processor called Sycamore uses superconducting qubits, which are artificial atoms that can store and manipulate quantum information. Sycamore has achieved a coherence time of about 10 microseconds for each qubit, which is enough to perform thousands of quantum operations before decoherence sets in. And Google has also demonstrated quantum supremacy with Sycamore, which means they performed a task that would be impossible for a classical computer to do in a reasonable amount of time. This task involved generating random numbers using a quantum circuit with 53 qubits and verifying their statistical properties. And another example of Google's work on decoherence control is its collaboration with researchers from Stanford University and UC Santa Barbara on developing a new type of qubit called a gnomon qubit. A gnomon qubit is a variation of a superconducting qubit that has a tunable coupling strength with its neighbors. This means that the qubits can be turned on and off as needed, which reduces the unwanted interactions with the environment and increases the coherence time. The researchers have shown that gnomon qubits can achieve coherence times of up to 75 microseconds and can perform high-fidelity 2-qubit gates. Google's research on decoherence control in quantum systems is not only important for advancing quantum computing, but also for understanding fundamental aspects of quantum physics. Decoherence is often considered a bridge between the quantum and classical worlds, and studying how it affects different types of systems can reveal new insights into the nature of reality. For instance, Google has used Sycamore to test whether quantum mechanics holds true at large scales by observing how entanglement decays with increasing system size. Google has also used gnomon qubits to explore how decoherence affects quantum phase transitions, which are sudden changes in the behavior of a system when a parameter is varied. Google's work on decoherence control in quantum systems shows that decoherence is not only a challenge, but also an opportunity for innovation and discovery. By developing new ways to protect and manipulate quantum information, Google is pushing the boundaries of what is possible with quantum technology and opening new horizons for science and society. However, Google has shocked the world by announcing that it's shutting down its quantum computer project. The company, which was one of the pioneers of quantum computing, said that it reached a fundamental limit in its ability to reduce errors and scale up its qubits. One of the main challenges of quantum computing is to maintain the coherence of qubits, the basic units of quantum information that can exist in a superposition of two states. Qubits are extremely sensitive to noise and interference from their environment, which can cause them to lose their quantum properties and introduce errors in the computation. To prevent this, qubits need to be isolated and cooled to near absolute zero temperatures, which requires sophisticated and expensive hardware. As stated before, Google has developed a quantum error correction scheme that uses multiple physical qubits to encode a single logical qubit, which could then be checked and corrected for errors. Google has demonstrated that using more qubits could lower the error rate of quantum calculations. However, this also increased the complexity and cost of the system, as there are more qubits needed to be connected and controlled. Now, Google has set a quantum computing roadmap for itself with 6 major milestones. The final one was to build a useful quantum computer by 2029, which could solve problems that are beyond the reach of classical machines. However, Google realized that it would need millions of physical qubits to achieve this goal, which was beyond its current capabilities and resources. Moreover, Google faced increasing competition from other companies and institutions that were developing their own quantum computers, such as IBM, Microsoft, Intel, Amazon, and IonQ. As such, Google decided that it was not worth continuing its quantum computer project given the technical difficulties and the uncertain market potential. The company said that it would focus on other areas of research and innovation such as artificial intelligence, cloud computing, and biotechnology. Google also said that it would collaborate with other players in the quantum field and share its expertise and infrastructure. The announcement of Google's quantum shutdown has sparked mixed reactions from the scientific community and the public. Some have expressed disappointment and sadness at the loss of a leader in quantum computing, while others have praised Google for its achievements and contributions to the field. Some have also questioned whether Google's decision was premature or motivated by other factors. This could give Google's competition the opportunity to overtake it. For example, Microsoft is working on building a topological quantum computer which uses exotic particles called anyons to encode and manipulate quantum information. This could potentially make the quantum computer more robust and scalable, but it also requires creating and controlling anyons, which is a major challenge. And Alibaba is one of the leading players in quantum computing in China, where the government has invested heavily in the technology. Alibaba operates a cloud-based quantum platform called Alibaba Cloud Quantum Development Kit, which provides tools and resources for quantum developers. Alibaba also collaborates with academic institutions and research labs on quantum projects. The future of quantum computing is still uncertain, as there are many open questions and challenges to overcome. However, there are also many opportunities and possibilities for further exploration.